I'm not professor, sorry. Hello, everyone. Today we are starting lecture number 9. This is a lecture about CAN extensions. I hope we will start and finish with them, but if something will be left, then it deserves time for next lecture too, for the next lecture, for additional time. So what is CAN extension? CAN extension, maybe you have heard about it. It's one of the maybe the most obscure but ubiquitous tools in category theory. It is a very known slogan of Saunders Mac Lane in his famous book, Category for Working Mathematicians, that all concepts are CAN extensions. As I remember, as the chapter starts with this phrase, as the whole chapter is named by this phrase. So everything pretty much what we are doing in math is a CAN extension. Today we will see why. Well, what is CAN extension? To give a precise definition and to start going quickly and deeply, I decided that we should look first at a motivational example. And the motivational example is just extension of a function. Well, right now we should start looking at motivation. Do you see the screen well? Okay, very nice.
Yeah, all good.
Thank you. So the motivational example is the following. Given a function from a set A to set E, function called f, we want to define an extension from a set B to set E, where A is a subset of set B. What is an extension? That when we take argument from a subset A into function f tilde, it behaves exactly as f. And diagrammatically, this looks as it's shown. Okay, this picture, I think it's very familiar for everyone. For instance, I will say that you can define a function. I don't know, well, one of the examples usually is drawn in books is definition functions from rationals to reals. So suppose we have rationals, they embed into reals, and also we have map from Q to R to reals, and this is just 2 to the power something. So 2 to the power a rational number. We can extend this function to 2 to the power something, but defined for all reals. Okay, this everybody can do. However, we won't necessarily obtain the exact formula. So 2 to the power for any real cannot be obtained. But we will define 2 to the power a real number x, so 2 to the power x, using limit. So we are using limit of 2 to the power some r over s, where r over s is approaching to x. So we are taking any approaching sequence to the real number x, and this sequence consists only of rationals. Why we can do this? Because rationals are dense in reals. So we can do this, but we still do not have formula, but this function exists. Okay, so this was a case for sets. And right now I want to go deeper precisely into categories. So what's the difference between setting of sets and setting of categories? So categories are sets where we have connection between the points. So in a pure set, we have just points. We have no arrows between them. So we don't care how different points relate to each other. So in one set, we can put an apple, an elephant, a bear, a noun, a pronoun. We can put ourselves, we can put the whole universe. It will be a set. We don't have relations. However, when we are dealing with a category, we need to have some arrows, or we want to have some arrows between elements. So we can't put any set of elements and say, okay, these elements are related with each other. No, in category should satisfy certain relations. Therefore, for pair of functors, right now I'm looking at the setup. For pair of functors f and k, we can't always state that there is an extension here, which is called f tilde. Or even if it is such extension, it's not necessarily the best one. Why? Because the functor k here can measure some I would say not defect, some imperfect, can have some imperfectness. For instance, two different objects of category A can go to the same element of B. So this mapping won't be injective. Or functor will say it's not faithful. It can be not full, so not every morphism in category B between images from category A or under the functor K will have all the morphism pre-images in A, and so on. So with functors, we have very different situations. And therefore, usually in this situation, we will be looking either from some approximation from F to F tilde composition of K to one side or another side. And these approximations will be called Ken extensions. We will later see that Ken extensions are everywhere and they define most of the concepts that we know. So let's start with the definition. So the definition number one, it's a left Ken extension. So given a diagram that we have of two functors F and K, we define Ken extension as a pair. First component of this pair is a functor from B to E, which called len, which is for left Ken. So left Ken is len from B to E, and the natural transformation from F, which called eta, from F to composition len of left Ken extension is functor K. Moreover, such a pair is universal in the following sense: that if we have any other pair, G and alpha, which is also which also reminds us picture above, then we can factor our two-cell alpha, so our natural transformation alpha, through eta in the following way: that we will draw this arrow, which is called left Ken extension, this functor. We will fill two-cell with eta, and we will find a unique, I will emphasize on this, unique psi, such that the following two-cell will be the original one. How we will simpler say this, that alpha equals psi k followed by eta. And this is a vertical composition of just natural transformation. So we have equality of two cells, or otherwise that our natural transformation alpha is divisible by natural transformation eta, which precisely constitutes the best approximation with left Ken extension. The dual notion is a right Ken extension. In this case, we will be approximating in a case when we have a map from composition of right Ken extension with K to F. So here in the first case, let me write it. We have eta, which goes from F to left Ken extension along K of F composition K. In the other case, we will have the converse situation. So here will be right Ken extension of F along K, composition K to F. So we have two different situations. Of course, these things remind us unit and co-unit. And we will see a little later, these are precisely unit and co-unit of some adjunction. So in this situation, you can think in the first case for left Ken extension, we are approximating F from outside. And in the second situation, we are approximating F. Here we have F, and we want to embed F in something bigger. Here is different situation. We have something smaller, and we want to approximate F from inside. Okay, right. So there from outside, here is from inside. So there F we embed in something bigger, and here something we embed inside F. These are precisely right and left Ken extension. Are there any questions to the definition? So what is factoring of cells or whatever? I wasn't talking about this too much, but maybe we should talk more about this. Sean, Shenyan, Rahul, anyone? Alan?
No, all good.
All good?
Yeah.
Okay. So then I will move my picture down and I will continue. Good. Let's start with a couple of examples. Okay, first I need to find where is my pen. Here is my pen. So I will have example number 1. So what will be example number 1 about? We will take trivial category 0. We will go to category of sets, and we are picking up a singleton. On the other side, we are mapping from 0 to category A, arbitrary category, and any such functor we know already picks up object A. Then who will be left-can extension? So we are looking for left-can extension. Left-can extensions should satisfy something universal, and this will be precisely, we can prove it, it will be a representable function. And what will be this natural transformation? So we need to go from star to A, comma, A. What we can pick up always from a home set from object to itself, of course, we can pick up 1. So this natural transformation is precisely 1 sub A. It consists only of 1 morphism, and it's 1 sub A. That's it. So we can write that A comma blank is a left-can extension of functor A, of functor star along object A. Of course, you will ask me, well, how did I do that? Well, let's spend a minute on this. So if we will pick up any other functor, so suppose we also additionally has functor, I don't know, let's call it G as before, then we need to pick up star. So we need to map 1 point set star of G of A. So, but elements in G of A are in 1-to-1 correspondent by UNEDA with maps from functor, representable functor represented by object A to functor G. Okay, so if this was X, this will be G blank comma X. So it's evaluating at point X of the image of functor of some morphism from A to something under the action of functor G. This is UNEDA lemma as I stated it on lecture number 2 or 3. And this unique arrow uses precisely the image of the identity morphism. So UNEDA lemma gives us this picture. Conversely, I would say that if you will take such picture, where we are picking up objects from the opposite category, we will have completely in a similar manner a representable functor, but contravariant one. And of course, here we have again 1 sub A. So it's a contravariant case of UNEDA lemma. So this one of the first occurrences of our CAN extensions. I would emphasize that both they were left. However, there are right CAN extensions. You can think yourself, what are right CAN extensions? By the way, you will ask me, when do they exist? So first of all, I stated some problem. I said that problem, if it has solution, this solution has name, but I never said anything about the case when does it have any solution. So about this, we are going to talk a little later. But before, I want to go to another part, which is called representation. As we saw, our problem has some universal solution, and to any universal solution, as for limits, colimits, we know that we can find some representation. So for limits, we found one functor, for colimits, another functor, and said that our cones or co-cone functor are representative. Similar case is with Ken extensions. That's why we will be talking about representations. Okay, so we have a picture. I will draw it again from A to category E and to category B. Here is functor K, along which we will be extending, and here is our functor F. Then, if here is functor G, and here is map alpha, then we have alpha going from F to GK. We can write this differently. Alpha belongs to the set of natural transformations in a category, in the functor category from A to E, from F to GK. Okay. Now I want to use again UNEDA. UNEDA, but for what? For the following function. So I can say that alpha belongs to the image of some object under certain functor. So who varies? This is this guy. G is variable. This is our variable. So we have a functor A in the functor category from A to E. Here we have functor F. Here we will have blank composition K evaluated at G. So here is our alpha. Okay. Then we will say that there is a functor A to E, functor category, from F to blank composition K, which takes any functor from B to E and lands in a set, in category of sets. So this is a functor. As we see before, as we just saw, by UNEDA lemma, alpha corresponds to certain natural transformation. Natural transformation. But who is this natural transformation? This natural transformation is from representable functor to our given functor. So our given functor, I will draw it with a red, is this one. So this is a functor. And this is an object. I know it's a functor, but for the functor in circled with red, this is an object to which functor is applied. So what natural transformation alpha corresponds to? It is a natural transformation from a representable functor, G comma blank. Of course, I am drawing a functor category because it's a home object, which is called alpha flat, we will call it, to A to E, from F to blank composition K. So by UNEDA lemma, this is one-to-one correspondence. The initial object in this case will be our Ken extension. So Ken extension is initial. Left Ken extension is initial among such natural transformations. Therefore, we have a statement which tells us that from B to E, here we have sorry, left can extension of f along k comma blank, there is an isomorphism with functor of natural transformations from f to blank composition k. Of course, this is all if len of f along k exists. So if left can extension exists, then this functor, which I am underlining right now, is representable. Representable by left can extension. The same trick as you remember I did with limits or colimits. Right now I did it again. So as you see, representable functors rule the situation. Are there any questions? Okay, if there are no questions, I will go down. But before, I would like to emphasize on the fact that here is why left can extension is called left. This functor is on the left. So in this isomorphism, we have a functor on the left. So that's why left can extension is called left. Okay. Then I will go down and where's my pen? Okay, probably write in 3 columns. It gets a little difficult for me. I need to write in 2 columns. Today I have a smaller screen than usual. Okay. And then another statement. It's about right can extensions that functors from B to E, functor category blank, comma, right can extension of F along K is isomorphic to from A to E. Here will be blank composition K to F. Everything changes, so it's a dual statement. And now we have a corollary. We have a corollary which says that if A, category A is small plus category E is bicomplete, and then we have the following adjunction. A to E, here will be B to E. So functors from B to E are multiplied by K, it's precomposition, so K upper star or blank comma K. And this functors has adjoint. Above is len left can extension. Sorry, no functor F. Functor F is variable, so you don't know what is here. And here is right can extension along K. Here is blank. So here we have a junction, and here we have a junction. So we have the 2 adjunctions, covariant adjunction. How we can see this? Just plug in any functor in the either of isomorphisms above, and you will see precisely the definition of a junction. So it's a corollary of both statements. Why I need a category A to be small? I think also B should be small because I'm working with functor categories A and B. If A and B are small, then functor categories will be locally small, so everything works. Without it, you will just have isomorphism. So, but not saying anything about functoriality in general because you don't have category structure. And another corollary, I would say that if K is fully faithful, then part A, E is iso, part B, epsilon is iso. Here for left can extension, here for right can extension. So if you have a fully faithful functor, then we will have isomorphism eta and epsilon. Okay, now we will have a couple of theorems that tells us how to compute Ken extensions if under certain conditions, so that these are existence theorems, and not only existence theorems for existence, but also computational formulas, how we can do that. To do this, I need a couple of additional auxiliary definitions. So, suppose A is, okay, not A, E. We will need E is co in parentheses complete category. Define A copower operation. So it's a bifunctor from set cross category E to category E, which takes set as object E and maps them to disjoint union, or no, sorry, for coproduct of E S times. So many times how many elements are in S. This operation I will denote using tensor. And B, power operation. Power operation is familiar and straightforward. We're taking set op cross E to E, and pair S comma E goes to the product S times of object E. This operation I will denote by cotensor. So notation that E is tensoring, and this pitchfork is cotensoring. Of whom? Of category E by category of sets. In our case, tensoring is given by power, copower operation, and cotensoring by power operation. Of course, here co in one case is on one side and on another side, but sorry, power operation, even if it's cotensoring, but power is a power. We can't call power copower just because we want, but we know what is a power. Okay, nice. So every time you see tensoring of any object of E by set, you mean that it's coproduct of this object S times. And the same with cotensoring, it's a power operation, so product of this object S times. Good. Now we can write down a computational formula. So theorem. Part A. If A, category A is small, category E is complete, that be co-complete. So on one side will be left, on other will be right, co-complete. Then left can extensions exist. So I will say lens. So all left can extensions exist and are given by formula. So we will write left can extension of functor f along k is given by coend category B ka blank tensoring fa. Of course, for you don't forget what we have. Here I have functor f from A to E, and I'm extending along functor k from A to B. So here is my len. Arrow is going down. Arrow you can extract from universal wedge. Sorry, co-wedge, because we have coend. If we want to evaluate at point B, you are plugging object B here where you have a blank under the coend. Under the coend, we always should think and check whether it is a proper bifunctor going from category A op cross A. So this variable is covariant, and here this variable is contravariant. So this is indeed a functor A op cross A to E. Also, object f of A belongs to category E. When we will plug any object from category B here on the empty spot, we will have home set, and therefore we are tensoring with a home set object of E. So this is a copower as we defined before. If one wants, you can of course write that it's coend over A. Here you will put a coproduct of f of A over B ka blank. If one wants, but that notation with tensor is, I would say, more suggestive. Also, I will use some other notation, which is, I would say, more convincing. It is this one. So we are tensoring two functors. First is this functor, second is this functor. One is contravariant in A, another is covariant in A. Okay. Then part B, of course, will be for right can extensions. If A is small and E is complete, then right can extensions exist and are given by formula. So ran k of f is given by beta sub k cotensor f, which is precisely the end over A, beta blank k of A, cotensoring of f of A which, if one wants, is n over A. Here will be product of object f of A. How many times beta blank Ka? Again, the same picture, but the natural transformation goes up. Are there any questions up to now? Okay, there are no questions, so I will move forward. So we have the notion of Ken extension. We know that they are given by, they can be defined as adjoint to precomposition with functor, along which we are trying to extend. And we know the formulas that exist in certain cases, in particular cases of complete or co-complete category. For complete category, we have right Ken extensions. For co-complete category, we have left Ken extensions. They always exist. Now, I would say that, as it's always written in books, that every notion which is Ken extension is so good as it has some additional property, which is connected to continuity in certain way. And this property is called being pointwise Ken extension. Some authors say that Ken extensions should be called weak Ken extensions, because the property that I just described is too, I would say, too unsuggesting. It's too not weak. It should be equipped with something else. And with what it should be equipped? With pointwise definition. So sometimes when people talk about Ken extensions, they actually talk about pointwise Ken extensions as the only extensions that deserve to be called Ken extensions that are pointwise. So now we will go to the part which is called pointwise. Ken extensions. And we will start with the following formula. Sorry, not formula, with the following definition. Okay. Definition. A functor from E to E prime called L preserves left Ken extension if every diagram, so we have functor f from A to E, we extend this by functor L from E to E prime category. We have extension functor K, and here we will have left Ken extension of F along K and natural transformation eta. So this diagram precisely is the diagram for the following left Ken extension. Here is K, here is B, here is LF, and here is left Ken extension of K, of LF along K. And here is eta prime. So when we will apply functor L to Ken extension, we will have Ken extension of L applied to functor F. Let's write it also the other way. So left Ken extension along K of LF comma eta prime precisely is L composed with left Ken extension of F along K comma L eta, where L eta is a whisker ring. So we see something as continuity. So continuity is when we can take function out of the limit. So limit of function is a function of a limit. Similar here, we have that functor preserves left Ken extension if it can be taken out of the Ken extension. So Ken extension of f, L composed with f is L applied to Ken extension. So similar definition is for right Ken extensions. Well, that's not surprising that I call this functor L, because we have a theorem that can be very easily proved that left in parentheses right adjoint preserve left Ken extensions in parentheses right Ken extensions respectively. So left adjoints we can swap using the adjunction formula from the left to the right and obtain the preservation of left Ken extension. Similar for right. So before we had that every left adjoint is co-continuous, every right adjoint is continuous when we studied limits and co-limits. That meant that left adjoint functor can be moved for inside the limit or outside of the limit without any pain. Similar story holds for left Ken extension. So left adjoints can be moved inside or outside Ken extension. And for right respectively, we have similar formula. Okay, now I will give a definition, which is a little, yes?
Sorry, I assume there's a way to realize your left and right Ken extensions as co-limits as limits respectively. Is that true?
It's of course true, and you are trying to get ahead of train. So this will be in a couple of minutes, but great point. And
I could prove this, right?
I would say that everything that preserves ends or co-ends will this or other way go to preserving Ken extensions, preserving limits, co-limits, preserving, I don't know, everything like co-uneda, uneda, whatever you want. So everything has either left, either right, I would say prototype. So for left prototypes, we use co-ends. For right, we use ends. So everything that preserves them, preserve all notions that can be described using them. Since co-end calculus is our main tool that was introduced a couple lectures before, then everywhere where appears ends or co-ends, we will think about something that preserves them. So limits and co-limits are particular cases of ends and co-ends. And here we go. You just saw that left Ken extension is what is co-end and right is end. Yeah. So if something preserve end is a particular case of limit, as we had before formula, how we can end or co-end reformulate as a limit using a category of elements. So everything that preserves co-limits will of course preserve Ken extensions. So I would say that it's like a circle. You know, all the notions can describe each other. And among these notions, the person should pick up the one that is the most useful. Among these most useful things appears to be end, because everything can be described using end and we can make calculus. That's why co-end calculus, not Ken calculus, not limit or co-limit calculus, and so on. That's why co/end calculus. But thank you for a question. That's very, very nice. And I would say you had deep thought in the correct direction. Thank you so much, Rahul. If anyone has another comments or questions, please ask anytime. I would love it. Okay, definition. Part A. Write can extension of functor f along K is called pointwise if it, sorry, somehow it's getting a little stuck. If it is preserved by all representable functors. And here the shape of representable functor, E, comma blank. What do I mean? Let's draw a picture. Here is A, going to E. From E, we are going to Z. Here is our representable E comma blank. Here is our functor F. Here is K. Here is our Ren, Kf. And here is epsilon. So this picture should coincide with the following. From A to Z, from A to B, here is K. Here will be the following functor. Again, I'm using the profunctor notations or Einstein notations that I used so many times today already. So the argument goes here. And here is our E, and here will be Ren, K, F, blank. And of course here some epsilon prime. I'm not writing which is it, it's obvious what it is. It's composition of a representable functor and epsilon. So it is pointwise if it's preserved by our representable functors. Okay, now you will ask me, what about left? With the left case, we'll have problems. Why? We want left be preserved by contravariant representable functors. But contravariant representable functors are going from opposite category. And still for left can extensions, we don't have any op in the diagram. So definition, part B. Suppose we have diagram A. Here is our E. Here is B. Let me draw A better, E better. Here's functor F, here's functor K. Right? Then we have here len K of F. Here goes eta. Now, this picture using op duality will be transformed to So here will be my len k f op. Sorry, maybe I am too much pressing on my board that it gets a little stuck. And here will be eta op. And here is k op. We know that left can extension is universal. And our cell eta is pointing downwards. When we are applying op, our cell eta op is pointing upwards. And it's again universal because op is a duality complete between A and A op. So everything that goes in one picture using op can be translated in opposite picture and conversely. Op changes the direction of two cells, but not one cell. So all functors are going still in the same direction, but two cells changing the direction. So from this, we are making conclusion. Conclusion is the following, that left can extension of f along k opposite is in fact right can extension of k op along k op of f opposite. Okay, so applying op to left can extension, we obtain right can extension, but arguments are opposite functors. That's it. So now we can formulate what is pointwise left can extension. So len kf is pointwise if ren k op f op is pointwise. So we move the situation from left case to the right case. In the right case, we described above. Since I don't want you to be confused, I will draw a picture. Okay, let me just exit my board for a second, okay? And enter it again because it's getting very slow. Sometimes it's using syncing, and syncing takes time. Also, I see I need a charger. So probably let's make 30-second break and I will plug in charger to my computer, okay? So 1 second. Hello, everyone, I'm back. Okay, so we are trying to get on our board where we just stopped. Come here, closer, closer. Okay, closer is better. So we have A op, oh, well, it's still, it's very slow. Here is going to E op, it is going to set. Here is functor E blank comma E, contravariant functor. Here is F op. Here is K op. And here is B op. And this is len KF and outside op, which is ren also. And here is arrow. Arrow, eta, opposite. Okay, so that's how you write pointwise left can extension. Now, in order to answer the question about limits and colimits, I will state a theorem, which is called colimit formula for can extensions. So limit and colimit formula. So we'll say colimit formula. It has, as usual, two parts for left and right. So part A, if for every object B in category B, there exists colimit of the following functor. So we are taking K over B. I will remind there's a comma category. K is functor, B is object. We are taking domain functor to category A. So we are just taking the index of the first component and then applying functor F to category E. Then it is this functor left can extension of functor F along K at point B. So if the following colimit exists, then we have for every object B, then we have left can extension and it's computed using this colimit. Nothing about pointwise was said. Part B. Part B. If for every B in B, there exists limit B over K to A domain E F, then it is right can extension of F along K at point B. So it's also an existence theorem. Before it was stated in terms of ends and coends. If you will use end and coend formula in proper way, so use a category of elements of certain functors, you will get this comma categories, K, B or BK. And you will have this formula. So if coends exist, they will give you can extensions. If this colimits limits exist, they will give you, again, can extensions. Okay. And now,
so the small b, does that mean the constant functor into the category B? That's it?
Again, who is constant?
You have two b's there, right? One is the category, one is an object.
Yes, yes. So here B is a curly B, and here B is an object.
But you're thinking of it as a constant functor, right?
Of course. So K over B is a category whose elements are K of A to B, and B here. B is constant. B equal B, A goes by a small to a prime. Here k of a prime goes to b, here equals, and here is k of a small. That's how morphisms looks in a comma category. So it's a comma category. Here b is a fixed object and k is a function.
Thank you.
So, of course, similar for b comma k. Okay, so these formulas give us left and right Ken extensions if they exist. Now, what is the connection with pointwise Ken extensions? The answer is the following. Part A, that right Ken extension is pointwise if and only if it is computed as, and let's call this formula, if you don't mind, 2 stars, and above formula 1 star. If it is computed as the mentioned limit 2 star. I will comment on this. B, left Ken extension is pointwise if and only if it is computed as 1 star, as colimit above. So now let's talk about the philosophy and like levels. You have Ken extension between categories. It can exist. It's super general thing. It does not oblige to be computed as coend, colimit, to be pointwise, whatever. It can exist. But if colimit exists or coend exists, which is the same as this colimit, just rewriting, then it is Ken extension. And then this Ken extension is pointwise. So Ken extension is pointwise if and only if it is computed as colimit or limit or coend to end equivalently. So in a whole class of Ken extensions, you take a smaller subclass that is described by limits and colimits, and they are called pointwise. So if pointwise exists, they are given by these formulas. If and only if. That's the main thing. So computational part is always pointwise, and conversely, if something is pointwise, it is computation. It can be computed using these computational formulas. One of the 4 formulas I mentioned. However, the categories can be super general, neither complete, neither small, whatever, as I stated in the beginning. And Ken extension still can exist. Is this clear? Other questions to this? So Ken extensions are above everything. Inside them are pointwise, and pointwise are good for properties and so on, for continuity, co-continuity, exchanging, and so on. Not otherwise. And then we can use formulas. However, I would say to you that if our category, target category E, has limits and colimits, so it's complete and co-complete or co-complete respectively, then we can compute these ends. The ends become colimits, and this is pointwise. So property of category E, where we target the extension and our original function, determines whether it will be pointwise or not. Of course, it can be done without this thing, but having property of category E, if it is complete, will give you all Ken extensions, which right Ken extensions. If it's co-complete, it will give you all left Ken extensions. And they all will be pointwise, both right and both left. That's it. So the deepest thing is property of category E. From property of category E will follow the formula. From the formula, not necessarily follow the property of category E. As you see on the theorem on the right, limit and colimit formula are stated in a way that if these limits exist, then they give like left and right can extensions. It's not, nobody obliges the whole realm of limits, small limits, big limits, whatever, if for category to exist, just these. But if they do exist, then we have them pointwise and so on. Okay, that's what I wanted to say about pointwise extension. Okay. Also, I have a small news for you. I think they will be nice. I did notes. So from previous lectures, I made notes. It's as image file, but they're very good resolution files, like 5 megabytes each. So today's lecture and to previous lectures, I will send along with along with the record to everyone in the next email. So you can have all your gaps filled if there are any. Okay, now I want to go to the next part, which is called all concepts are CAN extensions. So all concepts are CAN extend. Okay, sorry, I have something in the chat. Thanks a lot. Okay. Thanks a lot from Rahul. You're welcome. Always you're welcome. Okay, first part which we will talk about will be co-limits. So how we can write co-limits as CAN extensions? Well, when we have a picture with these 3 arrows, A, E, B, here is F and K, we will have some trivial cases, right? Okay, maybe let me write it a little on the other spot. So here on this side. Again, A, E, B, F, K. So in case when K is trivial, we'll have co-limits. What does it mean trivial? K is a functor from A to a terminal category 0. So if we have such functor, I will write precisely down, we'll have co-limits. That's a trivial story. Okay. Then B. If F is trivial, then I will disappoint you. Nothing interesting. Then our CAN extension will be also trivial. Well, nothing really to extend. No natural transformations. I mean, to be natural transformation from one point to the same point in the same category, 0. So here is nothing interesting. Part C. If we have functor K being identity, or here, then we will have that len along, sorry, A, that len along this identity is identity. So len of F, being more precisely, is F. So along identity functor, there is no extension because extension is the functor itself. Left or right, The similar for len and for n. Part D, if A is identity, trivial function, I mean, not trivial, identical function, then we have co-Yoneda. So both Yoneda and co-Yoneda. No. Sorry, I did wrong. We will have adjunction. Because we will have from identity to composition and from composition to identity. We'll have adjunction. And co-Yoneda is previous one. So this trivial case. So part B is completely not interesting. We'll cross it out, and all other parts we will describe. So first, co-limits. So we have A to category E. Here we'll have to 0. This is a trivial functor. This is a functor f. Then we have that len of f along shrink is a colimit of f. Similarly, f from A to E, here is again shrink, trivial functor, but now upper, so it's right can extension. That gives us limit of f. That's it. Funny, but a little boring. Part D, adjunctions. So for adjunction, we need not only unit and co-unit of adjunction, but also triangle identities. But triangle identities will precisely mean that the Can extensions that I will write down are preserved by certain functors, left or right adjoint functors. So we have here L from A to B. Here is epsilon, here is eta. Here is functor R is an adjunction. If and only if R comma eta is len of identity on A along L, plus it is preserved by L. And again, this is all equivalent to L epsilon is a ren of 1 on category beta along R, plus it is preserved by functor R. So adjunctions are described using Can extensions that are preserved by something. Okay. Then next part, part C, part B we are missing. It's co-Yoneda. So what we'll have here? We'll have here from A to set given functor f. Here is going identity functor from A to A. So len of F along identity is F. Similar story for always you should draw arrows, not to forget what can extension you're working with, left or right. Similar story is for right. So here is right of F equals F, arrow going up. Okay, so where is Yoneda, where is co-Yoneda? So ran of 1 along F can be described using AND, can be described using AND as in AND over X, A blank X, cotensor F of X. But in case of sets, this cotensor is given by such formula, and integral, and of set of such type is precisely set of all natural transformations. It's all coherent calculus, this couple formulas that I did before with you. It's blank here. Let's write double blank, and here will be F double blank. So natural transformations are in lower variable, and upper variable is where we compute our RN, but our RN is precisely F. So you have Yoneda. For left, we don't have such nice formula as natural transformation, but it's still nice as itself. So it will be coend over X, and here will be A lower blank upper X tensor F of X. And for sets, this tensor is given by coproduct. So this is copower. So here, this case is co-Yoneda. Okay, then to finish the story, I will write C prime. It will be a little surprising if I won't emphasize on it, that what's the point of it. So this will be called generalized co-Yoneda lemma. So what it tells us? Part A. I need to draw a picture. So I'm doing the same story as before, but I'm extending functor F, which lands in arbitrary category E, not in set. And there, I will be looking for len and ren for it. So part A, it's Yoneda part. So if category E is complete, then F is isomorphic to the end over A here blank, cotensor FA. As everything as I said above, but this object belongs to E. So this cotensor is precisely a power, because we have that category E is complete. If it's complete, it has all products, and products are cotensors. And these products are given by powers. Part B, it's co-Yoneda. In case when E is co-complete, we have the following. F is isomorphic to the coend. Here will be A comma blank, tensor F of A. Where this tensor is, in this case, copower. The difference, as it was before, is that category E can be arbitrary, but it needs to be complete or co-complete. Category of sets is both complete and co-complete. Therefore, this result generalizes usual Yoneda and co-Yoneda lemmas. Still, very often people work with functors that are landing not necessarily in a category of sets, in some other category, maybe with sets with additional structure, but not necessarily sets itself. Still, you have analog of Yoneda and co-Yoneda lemmas. You can try this using natural transformations, because for natural transformations, we use the trick that power will be given by set and end of set from one functor to another. It's natural transformation between these two functors. Otherwise, we can do this. Now, there is one small thing left, a half page, but I don't think that, I think I will do this next time. That's called density theorem. And now I will write to you a couple of remarks with which we will close today's lecture. So remarks. First remark. All formulas not correctly. All co-and formulas for LAN or RAN hold in an enriched setting. Well, the main is that len kf is b k tensor f, ren k f, it is b sub k cotensor f. And they are given by, first one is given by end something. The second one is given by end. So coend and end, and we know how to compute them in enriched setting. Second of all. Second of all is the following. 1 second, let me think. For len ren, we have assumed that certain co-limits exist in E. So for if category E has certain types of limits and co-limits, lens and rens exist. 3. The most important notions are Ken extensions. I wanted to say something else. Give me a second. I'm trying to recall. Well, I can't recall right now, but next time I think we will add something that is called density theorem, which states that every presheaf is a limit of representable presheafs. It's a very powerful result, which allows you to substitute your presheaf with representable presheafs if you can take the colimit out of it. And also, one of the corollaries of this result is the following, that when we are trying to compute left or right Ken extension along arbitrary functor K, it will boil down that we need to know how to compute Ken extensions along Yoneda embeddings, covariant or contravariant one. So the story is the following. You will know how to compute Ken extension of some functor from category A to category E if you can extend it, to its free co-completion. And free co-completion is category of presheafs. So you embed your category as representable presheafs, or in our case, it's representable prefunctors, in your functor category of presheafs. That it is called also free co-completion. We won't be talking about this topic, but in general. And there you extend. And it doesn't matter which is category B actually is. Only thing that matters if you can extend from presheafs and how you will do that. So this is called Len and Trent factorization formulas. So once you know how to do this, you are done. As you saw today, I put no restriction on category B. Once it was a restriction, that it should be small to have an adjunction, also on category A. So all the story goes in the target category E. And once we know its properties, we can have Ken extension. So what's next time will be not only density theorem, but we will have my favorite profunctors. People also like how I pronounce them. Yes, it will be a lot of profunctors, Rahul. I don't know how much we will have time to cover, because to cover everything I know and I like to talk about them, probably will need a month. But the most important things will be there. If you have any questions, you are welcome to ask, and thank you so much for your attention. I'm stopping the recording.